In the silent heart of a distant star, where hydrogen trembles under unimaginable pressure, a single photon is born in violence. Its creation is a moment of chaos, the collision of charged particles, the furious release of nuclear fire, the roar of fusion shaping the star's luminous breath. Yet the photon itself carries none of that fury. It slips free in perfect quiet, a weightless traveler pushed outward through layers of blazing plasma, rising slowly toward the surface like a spark carried by a storm. When it finally escapes the star's final veil, the noise of its birth falls away. Before it stretches an ocean of darkness so wide and so empty that even time seems reluctant to move. Interstellar space, a realm where entire cubic meters may hold only a handful of wandering atoms, where gravity weakens into whispers and silence becomes the dominant force. Here, the photon accelerates to the one speed the universe allows it, not by choice but by nature, racing into a darkness it will cross without ever aging a moment. It drifts through cosmic voids large enough to swallow galaxies, through regions untouched since the earliest epochs of the universe. It passes relic radiation from the Big Bang, the faint afterglow of creation itself. And though it carries no voice, it carries memory, the story of its origin imprinted in a vibration, a color, a frequency. Yet this quiet traveler poses a question older than science. How does something so small move through absolute emptiness without slowing, without changing, without experiencing time at all? Why does it exist as both wave and particle? And why does its motion carve the very structure of spacetime? Every photon traveling through eternity is a witness to everything, yet belongs nowhere. Long before equations measured the trembling fabric of space-time, before telescopes gathered ancient starlight from galaxies forming at the edge of visibility, humanity struggled with a simpler question: what is light? It appeared ordinary, familiar, woven into every waking moment. Yet its true nature hid behind an illusion of simplicity. The earliest thinkers sensed this hidden depth but could not yet grasp its scale. To them, light seemed as immediate as breath and as elusive as thought. In ancient Greece, philosophers stood beneath the sun and argued over the mechanism of sight. Some believed vision was an act of emission, that the eyes themselves released a subtle fire, reaching outward to touch the shapes of the world. Others insisted the world sent impressions inward, carried by something that moved faster than thought. Though these debates lacked the precision of later science, they revealed an intuition that light was more than illumination. It was a traveler, moving between objects and minds, slipping across space with a quiet purpose. Centuries later, in a world reshaped by new ideas and meticulous scholarship, an Arab scientist named Ibn al-Haytham placed light under a sharper lens. In the early 11th century, he envisioned experiments not as philosophical exercises but as structured tests of nature's behavior. Through dark chambers, mirrors, and controlled openings that allowed single rays to pass, he uncovered a truth that would form the spine of optics. Light entered the eye, not the other way around. This was a turning point, a recognition that light was a substance traveling independently, carrying the form of the world through space. It moved in straight lines, obeyed predictable rules, and revealed that vision was a receiving of distant information. For the first time, light had become measurable. As centuries flowed forward, scientific curiosity intensified. In the 17th century, Isaac Newton shattered a beam of sunlight with a glass prism and watched it unfurl into a spectrum of colors. Red, orange, yellow, green, blue, indigo, violet, an entire hidden world revealed in a single crack of refracted brilliance. It was the first undeniable proof that white light was not a unified phenomenon but a delicate composition of many. Light was not merely brightness, it was structure, frequency, and order. Newton believed light consisted of small particles, corpuscles, traveling in straight lines. Yet others, like Christian Huygens, argued for a wave-like nature, proposing that light rippled across an invisible medium just as sound traveled through air and water. This clash, particle or wave, would echo across centuries, hinting at a deeper enigma waiting to surface. Still, even the boldest early thinkers could not yet imagine the universe through which light traveled. For them, emptiness was a void lacking substance. But to explain waves, Many physicists imagined a mysterious medium filling all space, a hypothetical luminiferous ether. It was believed to be everywhere, weightless, silent, and undetectable, and yet essential. Light, they reasoned, must ride upon something. Then, in the 19th century, a Scottish physicist transformed the understanding of nature with a set of equations so elegant they still stand at the heart of modern physics. James Clerk Maxwell united electricity and magnetism into a single framework and revealed that changing electric and magnetic fields could generate waves that moved through space at a precise, universal speed. This speed matched the speed of light itself. Light was electromagnetic, but Maxwell's equations held a deeper implication. They described a wave that did not require any medium at all. The mathematics showed that light would move through empty space by the very nature of the fields themselves, independent of anything outside them. The idea was revolutionary, too revolutionary for many to accept. The ether was still presumed necessary. Waves without a medium seemed unthinkable. It was not until the late 19th century, through the experiments of Michelson and Morley, that the ether finally began to crumble. They attempted to measure Earth's motion through the hypothetical medium using precise interference patterns of reflected light beams. But the expected signature, a shift in light's behavior as the planet moved, never appeared. The result was a quiet negation. If the ether existed, it left no trace. Light seemed to move the same way in every direction, no matter how Earth traveled. This discovery deepened the mystery. How could a wave travel through emptiness without resistance? Why did light behave as though space offered no influence at all? The turning point arrived with a young patent clerk studying the nature of time, space, and electromagnetism. In 1905, Albert Einstein reshaped physics by accepting something others resisted. The speed of light, as predicted by Maxwell, was truly constant. Not constant relative to motion, or to the observer, or to any surrounding medium. Constant, absolutely. This was not merely a scientific refinement. It was a rupture. If light speed was unchanging, then time and space themselves must shift around it. Hours would stretch. Distances would contract. Simultaneity would dissolve. Einstein's special relativity proposed that light was not just another phenomenon. It was the foundation upon which reality was built. The photon, the quiet traveler, became the ultimate speed, the limit that defined the structure of the universe. Einstein's insight forced a profound realization. Light does not need a medium. It does not depend on the motion of its source. It does not slow in emptiness. It simply travels, always at the same relentless pace. But as soon as this truth was accepted, the mystery deepened again. How does something so fragile, so easily bent by gravity and scattered by matter, move through nothingness at a speed the universe protects at all costs? Why does it behave both as a particle and as a wave? How can it cross billions of light years without aging a moment? By the early 20th century, the study of light had traveled far beyond the curiosity of philosophers or the controlled experiments of optics. It had become a window into the structure of existence. Every breakthrough had peeled away a layer of familiarity and revealed something stranger beneath. What began as an attempt to understand vision had transformed into a revelation about the architecture of the cosmos. Scientists began to recognize that light was not merely illumination. It was information. It was geometry. It was the silent framework that connected distant corners of space into a single, coherent universe. Every star, every galaxy, every nebula, all became visible only through the paths traveled by ancient photons, survivors of unimaginable journeys. And with that recognition came awe. The simple question, what is light, had become a profound doorway into a deeper truth. Light was not just something that moved through the universe. It was something that defined it. The mystery had shifted from observation to reverence. Light was no longer a passive traveler. It was the quiet architect of reality. The early 20th century opened with a quiet crisis. It emerged not from catastrophe or failure, but from a contradiction so delicate and precise that it threatened the foundations of physics. At its heart stood a single number, a speed measured in the vacuum of space. 299,792 kilometers per second, a value so specific, so immovable, that it defied the expectations of every physical intuition humanity had ever known. In the world of ordinary experience, motion depends on context. A running river slows or accelerates depending on the current beneath it. Sound rises and falls with the density of the air it travels through. Even bullets fired from trains gain or lose speed depending on the motion of the machine that launches them. Everything in nature appears bound to its surroundings. Nothing moves independently of the medium it inhabits. Yet the light that fills the universe does not obey this rule. It refuses to be influenced. Its speed remains unchanged, whether measured from a moving Earth, a spinning satellite, or a distant star hurtling through the galaxy at tens of thousands of kilometers per hour. This was the shock that confronted Albert Einstein with stunning clarity. If the speed of light was truly constant, then the universe could not operate according to the assumptions scientists had relied on for centuries. Either the constancy was an illusion, or space and time themselves were malleable in ways no one had imagined. Einstein chose the unthinkable. He accepted that time and space were not fixed entities. They were flexible, fluid, and deeply intertwined, and they would distort themselves to preserve light speed. This decision fractured classical physics and opened a door into an entirely new understanding of reality. If light could not slow down, then time must bear the burden. Clocks moving at high speeds would begin to tick more slowly. A traveler racing near the speed of light would experience hours while the universe around him endured centuries. This phenomenon, time dilation, was not a theoretical curiosity. It became measurable decades later in speeding subatomic particles, in the ticking of atomic clocks carried aboard orbiting satellites, and in the aging of astronauts returning from space. Then came length contraction, the realization that distances themselves would shrink along the direction of motion as an object approached the speed of light. A spacecraft accelerating toward relativistic speed would find its path shortening, the cosmos compressing itself in front of the vessel. At high enough velocity, the universe would flatten and narrow, allowing the traveler to cross vast distances in far less time than expected. These distortions were not symbolic. They were physical consequences of a deeper truth. Light speed was a kind of cosmic anchor, a value so fundamental that the universe bent itself to preserve it. But perhaps the most disorienting consequence was the relativity of simultaneity. Events that appeared simultaneous from one vantage point would occur in different orders from another. The universe no longer offered a single, universal now. Each observer carried their own timeline, shaped by their motion relative to the eternal traveler, light. This realization was terrifying to many early physicists. It meant that time was not absolute. Past and future blurred at their boundaries. Existence itself became a woven tapestry of perspectives, none of them incorrect, none of them privileged. Humanity had been forced to abandon an intuitive picture of reality and accept one that echoed the behavior of the quiet light crossing the void. And then came the next shock, one that deepened the mystery further. If light traveled through space without slowing, without requiring a medium, what happened to a photon during its journey? Experiments revealed an astonishing truth. A photon does not age. From its own frame of reference, if such a thing can be imagined, no time passes at all. The moment of its emission and the moment of its absorption are stitched together into a single, timeless point. For light, the universe is not a sequence of moments. It is an instantaneous crossing. Photons released at the dawn of the cosmos, more than 13 billion years ago, have been drifting through the cosmic dark since long before the formation of Earth, yet they have not experienced even a fraction of a second. They do not decay. They do not tire. They simply continue, carrying the cold memory of the early universe on their backs. The cosmic microwave background, the oldest light detectable, is filled with these ancient travelers, each one a silent witness to the birth of structure itself. The shock intensified when scientists observed that photons could cross unimaginable distances without changing energy in any classical sense. They were not slowed by friction. They were not scattered by emptiness. Even in the vast cosmic voids, where entire galaxies disappear into distant specks, light moved without resistance. A photon might travel a billion light-years before touching a single atom, yet it remained pristine, unmarred, unchanged. This behavior contradicted every instinct shaped by life on Earth. In the world of matter, everything ages. Metals bend. Rocks erode. Stars collapse. Even the universe itself stretches and evolves. But light, the very messenger of cosmic history, appears immune to time's weight. How could something so fragile, so easily scattered by gas and dust, resist the passage of time entirely? Einstein's equations offered one explanation. At light speed, time ceases to flow. The photon does not live through a journey. It simply exists at both ends simultaneously. Yet this raised a deeper paradox. How could something that never experiences time travel for the entire age of the universe? How can a particle with no internal clock carry the history of galaxies and stars across billions of light-years? The shockwave of this realization swept through the scientific community. Light was not merely fast, it was foundational. It dictated the geometry of space-time. It shaped the boundaries of causality. It determined what could influence what, and how quickly information could spread across the cosmic ocean. It was the ultimate constant, the law that even the universe itself could not break. And yet the traveler remained silent, unchanged, untouched by the eons it crossed. The chapter closes on a paradox that continues to echo through modern physics. Light moves through eternity, yet never ages. A photon born at the dawn of time is still, in a sense, there, still carrying the moment of its creation, unchanged, unweathered, untraveled in its own perception. The universe ages, expands, evolves. Stars ignite and die. Galaxies collide. But light, the quiet witness, slips through eternity untouched by time, leaving physicists to confront a question that defies common understanding. How does something that never ages traverse the endless depth of the cosmos? Across the long history of physics, few subjects have grown stranger the closer scientists looked. And yet, among all the forces and particles that shape the universe, light stands alone. It behaves simply enough to guide migrating birds and illuminate ancient cave walls, yet remains complex enough to unsettle the foundations of modern physics. With every discovery, the puzzle deepens, rising like a tide that reveals more darkness rather than clarity. It begins with an impossible feat that no classical object could perform, a photon's ability to slip through barriers it should never cross. Quantum tunneling. In the familiar world, a ball thrown at a wall either bounces back or breaks through. But in the quantum world, the photon does something profoundly different. It approaches a barrier, hesitates in a haze of probability, and then appears on the other side without ever passing through in a classical sense. To the mathematics of quantum mechanics, no laws are broken. But to human intuition, the event borders on sorcery. Nothing with energy should cross a wall it cannot overcome, yet the photon does, quietly, endlessly, as if the universe permits it to ignore every rule except its own. And the strangeness does not stop there. In darkened laboratories, photons reveal another secret. They can interfere with themselves. When sent through two slits at once, a single photon paints an interference pattern, suggesting it behaves like a wave, exploring both paths simultaneously. But when detectors are placed to observe which slit it truly passes through, the interference vanishes. The photon chooses one route as though it knows it is being watched. The wave collapses into a particle, and the universe switches script. What was fluid becomes sharp. What was everywhere becomes localized. Physicists learned to describe the phenomenon without ever fully understanding it. Reality, at its smallest scale, appears to rearrange itself depending on how it is observed. And at the heart of that shifting landscape sits the photon, an entity that refuses categorization, a messenger that embodies the contradiction of being both spread across space and pinned to a single point. But the mystery grows deeper still. Photons can become entangled, paired in such a way that a change to one is mirrored instantly by the other, even if galaxies lie between them. Experiments across Earth, from Switzerland to China's Mishia satellite, confirm this uncanny behavior with extraordinary precision. Entangled photons share a correlation that violates every classical expectation. No signal travels between them, yet the symmetry remains. It is as if the photon remembers a connection that never weakens, no matter how wide the separation becomes. With these abilities, light reveals itself not merely as illumination, but as an architect of the universe's grandest structures. The cosmic web, a lattice of dark matter and galaxies stretching across billions of light-years, is traced and measured through the glow of ancient quasars. These hyperbright beacons, powered by supermassive black holes in the infant universe, emit photons that journey through the intergalactic medium, mapping its filaments and voids. Without light's endurance, this cosmic architecture would remain invisible, lost in the darkness between clusters. And in the violent heart of distant galaxies, gamma-ray bursts erupt with energies that defy comprehension. Their photons slam across expanses larger than galaxy superclusters, carrying information about magnetic fields, star collapse, and the fabric of spacetime. These photons travel billions of light-years, surviving encounters with cosmic dust, gravitational wells, and the thinning edge of the observable cosmos. They reach Earth telescopes with signatures intact, as if the universe itself protects them. Light also responds to gravity in ways that defy its massless nature. When photons pass near galaxies or clusters, their paths bend, forming perfect arcs and rings. Einstein rings. They arise because mass warps spacetime, and light obeys the curvature. Telescopes observe these distortions routinely, using them to map dark matter, a substance that does not emit or absorb light, but sculpts its path. In this way, photons become cartographers of the invisible, revealing the contours of forces humanity has yet to fully explain. Yet even with all of these behaviors, tunneling, interference, entanglement, gravitational obedience, the escalation begins not in what photons do, but in what they contradict. At the quantum scale, light behaves like a cloud of probabilities, uncertain and malleable, governed by wave functions that evolve until observation collapses them. It is a realm of chance, where outcomes become real only when measured. In this domain, the photon is unpredictable, a whisper of potential. But in relativity, that same photon becomes something entirely different. It follows exact geodesics through spacetime. It carries momentum precisely described by Maxwell's equations. It travels at a constant speed, unchanging and absolute. Its behavior becomes deterministic, calculated, and smooth. No probabilities. No wave function collapse. No ambiguity. Two frameworks, quantum mechanics and general relativity, describe the universe with astonishing accuracy. They underpin everything from particle accelerators to GPS satellites. They are the pillars of modern physics. Yet when asked to describe a single photon, they fracture. Each theory explains part of the behavior, but not all. Quantum mechanics reveals the photon's uncertainty, relativity reveals its unwavering precision. Between them lies a contradiction that refuses resolution. For more than a century, physicists have tried to bridge this gap. They've proposed quantum gravity, string theory, loop quantum gravity, emergent spacetime, and holographic principles. They've used particle colliders to smash photons into each other at energies high enough to glimpse virtual particles. They've studied cosmic radiation left over from the Big Bang, seeking clues in the polarization patterns of ancient light. They've measured the photon's properties with such accuracy that any deviation might hint at new physics. But no deviation appears. The photon follows both rulebooks, even though those rulebooks disagree. This is the escalation, the point where the mystery does not fade, but grows sharper with every breakthrough. The more scientists learn, the more the contradictions intensify. The photon is at once the most familiar particle in the universe and the least understood. Consider its dual identity. In quantum mechanics, a photon cannot be said to exist at a definite point unless measured. It is a probability distribution, a wave across all possible states. But in relativity, it follows a defined trajectory known as a null geodesic, a path that can be traced with exquisite precision. One theory says it is mostly indeterminate. The other says it is perfectly determined. Both are confirmed by experiment. Neither can be discarded. This conflict sits at the heart of modern physics. It is the fracture line between the quantum world of the very small and the relativistic world of the very large. Nearly every attempt to unify these frameworks, from Einstein's lifelong search to the current work of theoretical physicists, revolves around the photon. Not because it is obscure, but because it is too perfect, too stubborn, too consistent in its contradictions. Even the vacuum through which photons travel adds to the mystery. Quantum field theory suggests the vacuum is not empty at all, but alive with fluctuations, virtual particles, and background fields. Relativity, however, treats the vacuum as smooth space-time, devoid of structure except where mass or energy distort it. And yet, photons glide through this something or nothing effortlessly, interacting with both interpretations but bowing fully to neither. The universe depends on this quiet traveler to tell its story. Light brings news from distant stars, from exploding suns, from galaxies colliding in the night. It reveals the geometry of space-time, the behavior of matter, the history of cosmic evolution. But it does so while refusing to fit into the very theories it helps confirm. And so the tension grows. The deeper scientists descend into the quantum world, the stranger light becomes. The further they stretch into the cosmic scale, the more predictable it appears. Light is both chaotic and orderly, both probabilistic and exact, both wave and particle. It embodies every contradiction physics has tried to reconcile. Among all the forces and particles humanity has studied, the photon stands at the crossroads of all known mysteries, a messenger from the universe that reveals everything except itself. And as each discovery adds a new piece to the puzzle, the edges of understanding fray. The truth seems close enough to grasp, yet always slips away. The story of light does not resolve. It only escalates. Humanity is left with the same quiet conclusion. The more the universe is illuminated, the deeper its shadows become. Across the vastness of the observable universe, the photon remains the most familiar traveler. It crosses the cosmic web, slips between atoms, weaves through magnetic fields, and glides across the vacuum with neither hesitation nor decay. Yet behind this simplicity lies a profound set of mysteries, puzzles that push the limits of theory and imagination. To understand light is to stand at the frontier of physics, where the universe reveals its laws in fragments, never all at once. For more than a century, scientists have constructed frameworks to describe the photon, each powerful, each incomplete. The result is a mosaic of understanding, pieces of extraordinary precision and pieces missing entirely. The journey begins with quantum electrodynamics, often regarded as the most successful theory ever devised. QED describes how photons and charged particles interact through the exchange of virtual particles, shimmering momentarily into existence within the quantum vacuum. Its predictions match experimental results to astonishing precision, in some cases, accurate to more than 12 decimal places. Every test reinforces its power. Every measurement confirms its elegance. Yet even this near-perfect theory carries gaps. QED can calculate the scattering of photons, the magnetic moment of electrons, and the subtle way light interacts with matter. But it cannot explain why photons experience no passage of time. According to the mathematics, a photon's internal clock never moves. A photon created in the earliest moments after the Big Bang reaches a telescope today as if no time has passed at all. The universe may have aged nearly 14 billion years, but for the photon, the journey is instantaneous. QED describes the interactions along the way, but it cannot tell why the photon itself remains unchanged. The next great pillar is general relativity, Einstein's masterwork. In this framework, light becomes something different. The boundary speed of the universe, the fastest signal nature allows. Its path curves around stars and galaxies, following geodesics carved into space-time by mass and energy. General relativity explains gravitational lensing, Einstein rings, and the bending of starlight around black holes. It reveals how photons dance along spacetime's curvature with perfect obedience. But relativity offers no insight into the quantum behavior that defines light at smaller scales. It does not address interference, tunneling, or entanglement. It treats the photon as a classical particle riding the geometry of space-time, a picture incompatible with the haze of probabilities described by quantum mechanics. Where QED wields uncertainty and fields, general relativity holds to smoothness and precision. The two frameworks form opposite halves of a cosmic puzzle, and the photon rests uneasily between them. A different perspective appears in quantum field theory, which reframes particles not as discrete objects but as disturbances within fields that permeate the universe. In this view, a photon is simply an excitation rippling across the electromagnetic field, a transient spike in a continuous ocean. The vacuum, far from being empty, is alive with fluctuations, virtual particles, and hidden structure. Light, according to QFT, does not move through nothingness. It propagates through a medium that is everywhere, a background whose properties define the speed of its motion. This description solves some mysteries but opens new ones. If the vacuum is a sea of energy, why does the photon pass through it without slowing? Why does it not scatter, decay, or lose momentum? The vacuum teems with activity, yet the photon glides as though in untouched silence. QFT describes the field but not the serenity of the photon's journey through it. Beyond these established frameworks lies a landscape of speculation, ideas that combine mathematics, cosmology, and imagination to explore what traditional theories cannot yet reach. One of the boldest is the multiverse hypothesis, which argues that the vacuum itself might not be universal. Each region of a broader cosmic landscape could possess different physical constants, different particle behaviors, even different rules for how light is allowed to exist. In such a picture, the speed of light, long considered an immutable constant, might be specific only to this universe's vacuum. Another universe could host a different electromagnetic structure, a different set of field interactions, and thus a different speed for its photons. If true, the photon becomes not just a particle, but a clue to the nature of cosmic variation. Its behavior hints at underlying properties that may be unique to this particular cosmic environment. Another frontier emerges from the holographic universe hypothesis, which proposes that space-time itself may be a projection, a three-dimensional illusion arising from encoded information on a distant boundary. In this framework, light becomes not merely a wave or particle but a carrier of information. Photons may encode the structure of reality, transferring data across the projected universe. Their speed could represent the maximum rate at which information can propagate across this fundamental substrate. Under such a view, the photon is not just a messenger of the universe, it is woven into the fabric of the message itself. Its strange behavior, from wave-particle duality to entanglement, may reflect the deeper rules governing information flow across a holographic surface. But even these vast ideas circle a deeper question. What if light itself defines the boundary between the classical world and the quantum realm? Everything slower than light experiences the passage of time, acquires mass, and obeys the clockwork march of causality. Everything at the speed of light escapes that flow, existing in a state where duration collapses into a single instant. Perhaps the photon is the dividing line, the threshold where the universe becomes something different, the seam between the familiar and the unthinkable. In this interpretation, photons are not simply particles. They are manifestations of the deepest symmetry in nature, the invariance of the speed of light. They mark the limit of how reality can evolve. Below that limit, objects experience time, length, and mass. At the limit, all of those properties dissolve. The photon becomes a symbol of the universe at its most distilled, a pure expression of motion without mass, existence without duration. This leads to another profound speculation. Does the photon define causality itself? The universe's structure of cause and effect relies on signals not traveling faster than light. Every event, every interaction, every unfolding of cosmic history depends on this boundary. If photons are the ultimate carriers of information, then the structure of causality is etched into their behavior. They do not just obey the speed limit, they create it. There are theories suggesting that causality itself emerges from deeper quantum processes, and photons might be the visible expression of that emergence. In such a view, the reason the photon does not age, does not decay, and does not slow is not because it defies time, but because it exists at the very foundation of time structure. It has no age because aging itself is a property that arises only below light speed. Even the vacuum, often thought of as empty space, becomes a field shaped by the photon. In high-energy physics, photons interact with virtual particles. In cosmology, they trace the structure of space-time. In black hole physics, they encode the limits of event horizons. The photon is present at every frontier, defining the boundaries between what can be known and what remains hidden. As scientists explore deeper, from particle accelerators to gravitational wave observatories, they return again and again to the same realization. The universe hides something profound in the quiet motion of its light. The photon is both simple and impossible, both obedient and untamed. It moves with unwavering speed yet refuses to conform to the equations that describe everything else. And so the speculation continues. Perhaps the photon carries hints of a deeper reality, a framework not yet discovered, where quantum mechanics and space-time geometry merge into a single, coherent description. A theory in which the photon is no longer a contradiction, but a key. Until that day, light remains the universe's most enigmatic traveler. It crosses cosmic voids without aging, tunnels through barriers as though probability were a doorway, entangles across unimaginable distances, and carries the story of the cosmos while concealing its own. The deeper physicists look, the more the photon reveals, and the more it refuses to be understood. In every beam of starlight, in every quantum spark, in every whisper of radiation left from the birth of time, the same truth waits in silence. The universe is not finished revealing what it hides in the motion of its light. Across the darkness of the cosmic ocean, light remains humanity's oldest companion and its most elusive guide. It is the one messenger that has crossed the entire history of the universe, carrying with it the faint stories of creation, collapse, and the unimaginable scale of space-time. Yet for all its familiarity, the photon is still a mystery, a traveler whose nature has never been fully understood. And so, humanity has built instruments of unprecedented precision, placing them on mountaintops, in deserts, on orbiting platforms, and across entire continents, all to follow this single, relentless voyager. Each device forms a new kind of eye, one capable of catching light after it has wandered for billions of years or after it has endured the most extreme environments nature can produce. The pursuit begins with the James Webb Space Telescope, drifting far beyond the influence of Earth's warmth. It observes not the visible glow of galaxies, but the stretched, reddened remnants of ancient light, photons that have traveled since the universe's earliest dawn. Infrared wavelengths carry scars of expansion. They reveal structures formed when the cosmos was only a few 100 million years old. JWST's mirrors, cold and delicate, unfold like the petals of a metal flower designed to catch the faintest traces of time itself. Here, light becomes a chronicle. It reveals primordial stars packed into unexpected clusters, galaxies that defy early cosmological models, and heavy elements forming far earlier than theories predicted. With every image, the telescope confronts scientists with evidence that the early universe was more dynamic, more chaotic, and more luminous than once believed. The traveler's story grows stranger with each photon captured. On Earth, a different instrument watches light in a far more hostile domain. The Event Horizon Telescope, a global array of synchronized radio observatories, does not simply capture photons. It uses them to map the edges of gravity's deepest wells. When this network gazes at a black hole, it observes light trapped in a tight orbit, circling the abyss just before being swallowed. These photons become sketches drawn at the boundary of no return. They trace the geometry of space-time twisted into its most extreme shape. The famous image of M87's black hole, a blurred ring surrounding a shadow, is built from radio light that spiraled around the event horizon, surviving only by chance. It is a portrait made from a photon's final defiance. Each improvement in the array sharpens this view, revealing the dynamics of magnetic fields and accretion flows. In these glowing rings, scientists hunt for deviations from Einstein's predictions, tiny hints that gravity may behave differently under crushing curvature. Elsewhere, buried beneath the soil of Switzerland and France, lies a machine that does not merely observe light. It creates collisions that reveal its quantum character. The Large Hadron Collider at CERN accelerates particles to near-light speed, smashing them together with immense energy. Among the debris, physicists study photon-photon interactions and rare processes predicted by electroweak unification. In these fleeting events, light becomes both participant and product, revealing the underlying symmetry of forces. Photon-photon collisions, once thought impossible in classical physics, now stand confirmed. Photons can interact indirectly through virtual particles arising from the quantum vacuum. These experiments probe the deepest structure of the electromagnetic field, offering clues about undiscovered particles or deviations in the behavior of known ones. Every collision is a controlled disturbance in the fabric of reality, a brief crack where the rules of the universe become visible. Yet even the LHC is only the beginning. The next generation of instruments will extend humanity's ability to chase the traveler still further. Laser interferometers, like those that first detected gravitational waves, are now being adapted for even greater sensitivity. Proposed designs aim to detect minuscule ripples in spacetime that may be caused by quantum gravitational effects. By measuring how laser beams shift over kilometers of vacuum tunnels, physicists hope to detect whether spacetime itself jitters at microscopic scales. Such evidence could unify quantum theory with gravity, a discovery that would reshape our understanding of the photon's role in the universe. Elsewhere, the upcoming Stage 4 cosmic microwave background experiments will map the faint afterglow of the Big Bang with unprecedented resolution. The CMB is not simply ancient light. It is a fossil, a whisper from the moment matter and radiation first decoupled. Slight variations in this glow may reveal whether the speed of light has always been constant. If the early universe obeyed different electromagnetic laws, those differences could be etched into the CMB as subtle temperature fluctuations or polarization patterns. In orbit and on the ground, high-energy gamma-ray detectors search for the most violent expressions of light: bursts from collapsing stars, flares from magnetars, jets from supermassive black holes, and particles accelerated to energies beyond human comprehension. These photons traverse distances larger than galaxy clusters, passing through intergalactic voids untouched. They test whether the universe absorbs or distorts them over unimaginable scales. Any unexpected dimming, time delay, or spectral shift could reveal hidden forces, exotic particles, or extra dimensions curled within spacetime. Each of these tools pursues the same set of questions that have haunted physics for more than a century. Scientists search for the limits of relativity, testing whether the speed of light remains truly invariant across all conditions. If even the smallest deviation appears, it would signal cracks in Einstein's framework, pointing toward a new theory of spacetime. They look for clues about quantum gravity, hoping that photons interacting near black holes or in high-energy collisions will expose the quantum structure of spacetime, an architecture too fine to be detected directly. They investigate whether the speed of light has ever changed, probing ancient photons to see if the constant truly remained constant during the early universe. If it shifted, even slightly, it would rewrite the foundations of physics, hinting at phases of cosmic evolution governed by different rules. And they search for signs of hidden dimensions, additional spatial layers predicted by theories such as string theory. These dimensions might subtly influence how photons travel, altering their energy distribution or introducing delays across vast distances. Light becomes a messenger from beyond the familiar three dimensions, carrying whispers from a deeper geometry. Across all these efforts, a quiet truth emerges. Modern science is no longer simply observing light. It is interrogating it. Every tool, from orbiting telescopes to underground accelerators, seeks to uncover the traveler's secrets, how it moves, what it reveals, and what it refuses to show. Yet the photon remains elusive. It threads through magnetic fields and gravitational wells without aging. It tunnels through barriers where no classical path exists. It carries information across billions of years, untouched by decay. Every experiment sharpens humanity's understanding, yet none resolves the paradox at the heart of the mystery. Light behaves as though it exists outside the flow of time, yet it shapes the evolution of everything within it. Still, the pursuit continues. In the quiet hum of observatories, in the synchronized timing of telescopes linked across continents, in the glow of data streams returning from space, the search deepens. Humanity listens for signals older than galaxies, for photons orbiting black holes, for radiation forged in the first moments after creation. Each measurement adds one more detail to a story written across the cosmos. And through it all, the traveler moves on, silent, unchanged, unhurried. For even now, after every discovery, after every theory, and after every instrument struggles to catch it, light remains ahead. It crosses the void long before humanity learns how to follow. It carries the universe's past while revealing the limits of understanding. The chapter ends where the pursuit continues. Humanity is still chasing the quiet light across eternity, trying to understand the traveler that defines the universe, and the universe that defines the traveler. Across the vast stillness of space, where matter grows thin and silence becomes a kind of cosmic atmosphere, light continues its long journey. It does not hesitate. It does not pause to consider the ancient distances ahead. It simply moves, carrying with it the quiet memory of everything that has ever burned, collided, collapsed, or sparked into existence. In this final chapter, the narrative slows, as if echoing the gentle persistence of the photons themselves. For scientists, philosophers, and all who contemplate the night sky, light is far more than a physical phenomenon. It is the universe's most patient storyteller, weaving together the saga of creation with threads that stretch across billions of years. Light is the messenger of stars. Every flicker arriving at a telescope mirror or striking the back of a human eye is a fragment of history, a faint echo from a world that may no longer exist. A supernova's fading glow describes the end of a star long extinguished. The soft infrared murmurs captured by space observatories reveal galaxies forming when the cosmos was still young, only a few 100 million years after the Big Bang. Photons that left their birthplaces in those primordial furnaces have traveled across the swelling fabric of space-time, stretched into longer wavelengths by the universe's relentless expansion. And when they finally arrive, they carry with them a message older than Earth itself. In this sense, the universe does not simply contain stories. It is a story, one written entirely in light. This chapter contemplates what it means to inhabit a cosmos where every truth available to humanity arrives through these tireless travelers. It explores the philosophical weight of this dependence and the emotional resonance of realizing that everything perceived, measured, or imagined about the distant universe comes filtered through the patient accumulation of ancient photons. For humanity, light is not merely illumination. It is memory made visible. Light, in all its quiet motion, defines the boundary between the known and the unknown. It sets the limit on what can be observed, understood, or inferred. The cosmic horizon, the farthest distance from which light has had time to reach Earth since the Big Bang, acts as a moving frontier of knowledge. Beyond it lies a realm forever unseeable through direct observation. No telescope, however powerful, can retrieve photons that have not yet arrived. No future experiment can gather messages that have not crossed the gap. The universe therefore reveals itself selectively, offering its history frame by frame, photon by photon. Humanity witnesses a cosmos of echoes. This strange dependence shapes every scientific understanding. When astronomers observe a distant quasar 13 billion light-years away, they witness its ancient youth. When they examine the faint red glow of the cosmic microwave background, they observe the universe as it existed a mere 380,000 years after the Big Bang, when atoms first formed and light was free to travel through space. These photons are not metaphors for the past. They are the past, preserved across unimaginable distances and time scales. Thus, the cosmos seen today is not the cosmos that exists. It is the cosmos that was. This realization carries both humility and awe. Humanity, for all its ambition to understand the universe, remains anchored to the present while relying entirely upon the ancient trajectories of light to reconstruct what came before. Every observation is a reconstruction, pieced together from photons that left their origins long before the emergence of life on Earth. Scientists are keenly aware of this paradox. Humanity perceives reality only as it was, never as it is. Yet this constraint is not a limitation of human capability alone. It is woven into the architecture of the universe itself. Light sets the speed limit of causality, the maximum rate at which information can be exchanged. It forms the backbone of relativity, defining what events can influence others and what remains forever isolated. Without this unwavering constant, the universe's structure would collapse into chaos. Space-time would lose its coherence. Cause and effect would blur. Instead, the cosmic order stands firm, guided by the steadfast march of photons across the void. This gives the photon a unique philosophical role. Its existence does more than illuminate space. It enforces the rules that make a coherent reality possible. It is not merely a messenger of events. It defines the very framework in which events can occur. Thus, light is more than a traveler. It is the boundary between classical and quantum worlds, between determinism and probability, between what can be known and what remains unknowable. At the quantum level, the photon behaves as both particle and wave, a duality that defies classical intuition. It has no rest mass, yet it carries momentum. It experiences no time, yet it interacts with the passage of time everywhere it goes. It emerges from the electromagnetic field, yet its behavior determines the structure of that field itself. Light is both participant and referee in the cosmic arena. Even human life is shaped by light in quiet, unnoticed ways. The circadian rhythms guiding biological clocks depend on the rising and setting of sunlight. Photosynthesis, powered by energetic photons, supports the entire food chain of Earth. And the evolving climate of the planet hinges on how light interacts with atmosphere, oceans, and land. Thus, from the microscopic scale of biology to the grand scale of galaxies, light is the thread uniting existence. The philosophical depth of this relationship is profound. If light is memory, and memory is the foundation of understanding, then the universe is continually offering its past to any civilization able to listen. The cosmos becomes a vast archive, and humanity one of its youngest interpreters. Astronomers often describe telescopes not as devices that look into space, but as instruments that look into time. With each new generation of observatories, from Hubble to James Webb, from the Event Horizon Telescope to the coming wave of interferometric arrays, humanity widens its access to the universe's recollections. These glimpses backwards allow reconstruction of cosmic evolution, the births of stars, the collisions of galaxies, the growth of black holes. And yet, for all these insights, the universe retains its mysteries. The earliest epochs, the inflationary moments after the Big Bang, remain hidden behind a wall of opacity. No photons from that era survive to be captured. Gravity waves may someday pierce that barrier, but until then, light defines the horizon of what the universe is willing to reveal. Thus, every scientific advance is, at its core, an attempt to understand the messages carried by light, messages encoded in wavelength, polarization, energy, and intensity. But behind each measured value lies a greater philosophical truth. The universe is speaking quietly, patiently, across the dark. What, then, does the quiet light mean for humanity? It means that every night sky is a living archive, a cathedral built from ancient radiation. It means that the universe has been documenting itself since the dawn of time. And it means that humanity, standing on a small planet in a random corner of one galaxy, has been given the rare gift of reading that archive. This awareness alters the perception of existence. For in the shimmering band of the Milky Way, or in the faint glow of a distant nebula, lie stories older than the Earth, older than the Sun, older than the atoms in human bodies. These photons began their journeys long before the conditions for life were present on this world. And yet they arrive now, as if waiting to be witnessed. Light connects humanity to a cosmic lineage that stretches back to the origin of everything. It means that the universe is not silent. It speaks through every photon that reaches a detector, a mirror, or a human eye. It narrates its own birth, its growth, its transformations. It whispers of distant worlds, collapsed stars, luminous clouds of gas, and the invisible structure of space-time. And perhaps most profoundly, it reminds humanity of its place in a universe far older and larger than imagination. As the chapter comes to its close, the pace slows again, mirroring the quiet persistence of light across the void. For all its speed, light is gentle in its arrival. It does not force its message. It simply exists, carrying a fragment of the universe's memory from one corner of space to another. The quiet light traveling through empty eternity is not merely illumination. It is the universe speaking, one photon at a time, across the infinite dark. And as long as light continues its journey, the universe will never truly be empty.